Achieving an optimal well design is key to maximizing production over the life of a well. The PIPESIM simulator enables engineers to analyze the key parameters that would influence overall well performance using the vital nodal analysis technique. In this demonstration video, I will show you how to build, run, and evaluate a well model. First, I will create a new well-centric workspace. The interactive well schematic appears on the left, and well components such as tubing, casing, or chokes can be dragged and dropped in place. First, I'll drag a casing from the insert ribbon and attach it to the wellhead. Next, I will add some tubing. I can either drag it from the insert ribbon or add a new row in the Tubulars tab. From the casing catalogue, I select some 7-inch casing. Next, I enter some tubing information directly: an inside diameter of 2.195 inches, a wall thickness of 0.34 inches, and a roughness value of 0.001 inch. Let's specify a bottom measured depth of 10,000 feet for the casing and 9,000 feet for the tubing. The well is a vertical well, so I'll leave the default vertical option on the Deviation Survey tab. I will also leave the defaults on the Downhole Equipment and Artificial Lift tabs for now. On the Heat Transfer tab, I will specify 65 degrees Fahrenheit as the soil temperature at the wellhead. We will specify the reservoir temperature next, in the Completions tab, and these two temperatures will define the temperature gradient from reservoir to wellhead. To add a completion, I will simply drag one onto the well schematic, or add a new row. Specify a completion depth of 9,500 feet. As you can see, there are a variety of inflow performance models to choose from. Let's select the Simple Productivity Index model and enter a reservoir pressure of 5,000 psia, temperature of 200 degrees Fahrenheit, and productivity index of 1. The IPR preview plot does not display yet because I have not defined the fluid model. Every completion, source, and injection point in the PIPESIM simulator must have an associated fluid. To create the fluid, I go into the Fluid tab and select New Fluid. I will pick the light oil and gas template and specify a gas oil ratio, GOR, of 500 standard cubic feet per stock tank barrel and a water cut of 25%. We can now see the IPR preview plot. I will check this box to use the Vogel model below the bubble point, and we can see that the IPR plot updates to show two-phase effects below the bubble point. Notice on the well schematic that the flow path is represented by green lines with arrows, and that fluid is producing through both the annulus and the tubing. To isolate the fluid flow to a singular path through the tubing, add a packer at 8,710 feet from the Insert ribbon, or by adding a row in the Downhole Equipment tab. Finally, let's add some surface equipment. To do this, I will go to the Surface Equipment tab and insert a choke and sink into the schematic, and connect them using a flow line. And then connect the choke to the wellhead using a connector. Next, I select the choke and enter a bean size of 128 to 64th of an inch, and select the flow line and specify a diameter of 3 inches and horizontal distance of 2,500 feet. With the well model complete, we can now run a nodal analysis. Nodal analysis enables you to determine how much production can be achieved, that is, the well deliverability. The PIPESIM simulator accounts for changes in fluid behavior, pressure losses across the flow path, and heat transfer with the surroundings, and enables you to sensitize on various inflow and outflow parameters to optimize the well performance. Before launching the nodal analysis task, or any task, It is a good practice to check to see if there are any validation issues on the validation center and resolve them before attempting to run the simulation. There are none, so the task can be launched. In the Home tab at the very top, I'll select the Nodal Analysis task. I'll be prompted to select the location of the nodal analysis point, and will select the bottom hole as the location. This automatically inserts a nodal analysis point at the bottom hole, which is the completion depth in this case. The nodal analysis point can be moved along the flow path to divide the system at any point into inflow and outflow. In the task dialog, let's enter an outlet pressure of 250 psi. Now I will click the Run button, which is now active to run the task. When the task is run successfully, a nodal analysis systems plot is displayed which shows the inflow and outflow curves, as well as the operating point. The operating point of approximately 2,000 standard barrels per day and 3,000 psi is the solution of the task, and is the flow rate the well would produce and the flowing pressure at the bottom hole nodal analysis point that corresponds to that flow rate. I can also check a box to display the bubble point, as well as the operating envelope for the well, which is bounded by the maximum erosional velocity ratio, user-specified maximum drawdown limit, reservoir pressure, and the inversion point for stable liquid production. I can also click the Profile Results tab to inspect the flowing profile variables, such as flowing pressure, temperature, hold-up, and many others, from the reservoir to the surface, corresponding to the operating point flow rate. The profile results can be viewed in tabular or grid format. You may also customize this grid for adding and removing variables of interest. Many parameters affect the operating point. Some of these are in the inflow, such as reservoir pressure and productivity index, and some are in the outflow, such as wellhead flowing pressure and tubing size. Sensitivity analysis on any of the inflow and outflow parameters can show their impact on performance. For instance, a sensitivity has determined that when the reservoir pressure drops to 4,000 psi in the future, the well will stop flowing at 80% water cut. We will now examine the option of installing an ESP to maintain well production when reservoir performance declines. I can choose to add a specific ESP to the well in the Artificial Lift tab, or do a proper ESP design using the ESP design task, which involves running the design to select the appropriate ESP to deliver my target flow rate, taking into account constraints such as the casing inside diameter. I will choose the former option and add an ESP at 8,956 feet. I will select an ESP from the catalogue that can deliver a target flow rate of 2,000 barrels per day. The catalogue has also been filtered to show ESPs that can fit into the casing with an ID of 5.92 inches. The recommended pumps have also been ranked in decreasing order of pump efficiency. I will select the DN 1800 pump, which is the most efficient for the design conditions. The performance and variable speed curves for the selected ESP are displayed on the right. 100 pump stages have been pre-populated, but it is important to note that this may be insufficient to deliver the target rate of 2,000 STB per day. I would need to run the ESP design task to be able to precisely determine the number of stages required to deliver the target rate. I will also apply the viscosity correction to correct the pump performance curves, which are based on water for the actual oil viscosity. A gas separator can be added as a component to the ESP if the well has a high gas volume fraction. This is not the case for this well, so I will leave the box unchecked. I will also select the stage-by-stage calculation option to ensure that ESP calculations are rigorously done, taking into account losses between the stages. I will now run the nodal analysis task to evaluate the impact of the ESP by configuring a sensitivity on the frequency, 0 Hz for the scenario without the pump, and 60 Hz for the pump on. The system results appear, and as previously determined, without the ESP, the well is dead. The benefit of the ESP is clearly seen in that it enables the well to produce at a rate of approximately 1000 STB per day with 100 ESP pump stages. To deliver the target rate of 2000 barrels per day, more stages would need to be added. This is one of the many different workflows that can be used to design, evaluate, and optimize a well using PIPESIM. Through nodal analysis, the PIPESIM steady-state multi-phase flow simulator enables engineers to understand well performance so they can design and optimize wells to ensure maximum deliverability.